Okay, so this is 6.5, parametric equations slash parametrization. This is a very important topic mathematically. It's used quite a bit to describe real-world phenomenon, to help us study real-world phenomenon using mathematics. We're going to only do the very, very basics of it, just to give you an idea for what this topic is about. But you'll see a lot more in the future, especially if you take calculus. All right, so the way we're going to present this is in terms of motion. So let's say I have the real world. Let's just say a two-dimensional real world. So maybe we're describing our motion on a map. All right, Google map from top down. All right, viewing from above. All right, so our motion, let's say, looks something like this. So we're starting out right there, and we're moving, maybe we're going east kind of, and then maybe we turn south, and then maybe we turn west, and then something like that. Okay, so this is our path, our motion over time. All right, so we're starting here. Let's say it's a drive. So we're driving east, then we turn right, then we're driving south, we turn right again, then we're driving west, and so on. All right. Okay, so how do we study this kind of motion mathematically? The idea is we want to also consider, so we have this here xy plane describing our position as we drive, but let's also add a time axis here, just separate from the x and y, where let's put t equals 0 here, 1, 2, 3, and let's say we're measuring time in hours, all right? Okay, so the deal is we can associate to every time a position in the xy plane. So for example, t equals 0, let's say, corresponds to the start of our drive, right? Where we are at the very beginning. So t equals 0 perhaps corresponds to that guy right there, right? So on the left is the time, and on the right is our position at that time, okay? For example, maybe 1 hour into our drive, we can put an arrow to, let's say, right there. So that's where we are after an hour, right? Let's say after 2 hours, we've driven, let's say we started driving really fast, and after 2 hours, we're here. And let's say after 2 hours, we've hit traffic, and from the time 2 to time 3, we've driven only a small distance. So there, all right? So maybe we have an arrow that goes from here to there, and then an arrow that goes from here to there, okay? So this picture here describes for us our motion, right? At time 0, we're right there. After an hour, we're right there. After 2 hours, we're right there. After 3 hours, we're here. Okay, and of course we can continue this going more hours, driving for more hours, or we can put in more points, right, in between 0, 1, 2, 3, right? So this is a decent visual representation of our drive, all right, of the motion, of our motion over time. Okay, by the way, negative time is also allowed. So if I have -1 here, this would be 1 hour before our start time, right? So maybe if we were already on our drive, 1 hour before we started, maybe we were here, okay? Or 1 hour before the official start time, all right? Okay, so this is a nice visual representation, or an okay visual representation of our motion. But first of all, it's a little messy. And second of all, how are we supposed to study our motion with pictures like this, right? Usually, we like to study things using formulas, using equations, right? With pictures, one big problem is, first of all, it's kind of messy. Second of all, pictures can be misleading. And, if I didn't draw this motion accurately, then, it's hard to tell exactly what's going on. All right, so we're going to want to describe this motion more mathematically. And the way we're going to do this is we're going to notice that at every time, right, we have a corresponding point in the xy plane, right? So again, at time 1, we're at that point right there, okay? So how do we describe this? Well, that point right there is described using two numbers, right? An x coordinate and a y coordinate. Okay. So what we have ultimately is every time, right, t equals 1, corresponds to a specific x and y coordinate, right? So let me label just this one here. 1, 2, 3, 1, 2, 3, 4, 5, 6, let's say. So this one is going to be at 3, 6. All right. So at time equals 1, our position is 3, 6. All right. And you can do this at any other time, right? At t equals 0, our position is whatever, something, comma, something. At t equals 2, our position is something, comma, something. At t equals 1/2, our position is something, comma, something. Okay. All right. So we have this association for every time t equals 1, we get a position, 3, 6. All right. Now let me write this in a slightly different way. T equals 1. At time t equals 1, we have an association to a position, but instead of writing it in parentheses in kind of coordinate form, let's write it as x equals 3 and y equals 6. All right. Okay, so this is how we're going to be working with our motion today. All right. So at every time, we have associated to that time an x number position and a y position. Okay. Now this works for every time. So if you think about this association, right, you can think of this left-hand side as the input to a function, and the right-hand side as the outputs of two functions, the x position and the y position. All right. So in other words, I can think of this as just to write the same thing in another way, t equals 1, right? If I put that as an input, then the output here is x. I think of x as a function of t, right? Because our position depends on time, right? Our position is changing in time as we drive along this road. So x of 1 is equal to 3, all right? Y of 1 is equal to 6, all right? And you can do this again for every other time. Let me just do another one. Let's say a simple one here is t equals, let's say t equals 3, right? At time t equals 3, we're at the position 1, 2, maybe minus 2, 0, right? So t equals 3 corresponds with x of 3, y of 3. The x position is minus 2. The y position is 0. All right. Okay, so essentially, what this discussion tells us is that we can describe our position in time using two functions, x of t and comma y of t, right? So these two together describe our position, position at time t. Okay. All right, so this allows us to use the techniques of math, because what we're doing now is, instead of drawing pictures, we're working with two functions, x of t, which describes our position in the x direction, horizontal direction, or east-west direction, and y of t, which describes our vertical position, or in other words, north-south position. All right. Okay, so now we can, if we have formulas for x of t and y of t, we can determine our motion at any point. We can actually determine our velocity at any point. We can determine our acceleration. Anything that we might want to study in terms of motion, we can study using those formulas. Okay. All right, so this is super powerful especially because if you have these functions, you can study real life physics. All right, so let me give an example of this. So let me write down one possible motion that we're making. Right? So let's say x of t is equal to 1 plus 3t, and y of t is equal to 2 plus 5t. All right. So these two equations here, these two functions here, describe my motion at time t, right? So what this says here, the way we interpret this is, at time 0, let me write it like this, t equals 0, we're at position x of 0, comma y of 0 in terms of coordinates, all right? So in this case, x of 0, I plug in 0 into my first equation, into my first function, I get 1. And when t is 0 for y, I get 2. Okay, so what this equation here, or this is called a parametric equation. What this parametric equation here tells me is that at time 0, I'm at the position 1, comma 2. So let me kind of graph this as well. So 1, comma 2. So I'm starting out here at time t equals 0. Let me label this t equals 0. Okay, let me write this here at t equals 0. That's where we are at t equals 0. So we can figure out our position at any time just by plugging in that time into the equation, right? So at time t equals 1, we're at x of 1, comma y of 1, right? And that's going to be just plugging in a 1 into the x function, I get 4. And plugging in 1 into the y function, I get 7. So we're at 4, comma 7, all right? So 1, 2, 3, 4. Or sorry, 1, 2, 3, so 4 is there, and 7, 1, 2, 3, 4, 5, 6, 7. So we've moved to here at t equals 1, all right? Okay, so with this formula, we can plot our position at any time, right? T equals 2, we can do another point, t equals 5, t equals minus 1, and so on, okay? So ultimately what happens is if we do plot our position at any time, for this particular example, it's going to be like this, all right? So what this is actually going to be describing is motion along a line, all right? And if you look at the two examples that we've given here, we're here at t equals 0, and at t equals 1, we've moved to here, right? T equals 2, we will have moved maybe up to here, and so on. So this set of formulas, this parametric equation here, describes motion along, let's say, a straight road in this kind of roughly northeasterly direction. Okay. So what happens here is, in fact, this is, of course, a straight line motion, and it's actually describing motion as we're moving with constant speed, okay? All right, we're not going to talk about speed too much or at all today, but from these equations, I can gather that our speed is actually related to this number 3 and that number 5 right there, all right? Okay, so this is nice, right? I'm now able to describe a drive using math, right? And again, if I want to understand how fast I'm driving, my acceleration, the direction that I'm driving, and so on, it all can be figured out from these two x of t and y of t's. All right. Okay. So maybe this isn't so exciting, right? It's just a straight line. But the really useful thing here is that we can describe any sort of motion in this way, right? So motion like this, right? Driving in that direction, we can describe it with some formulas, x of t equals something, y of t equals something. And then we can study it using math by studying the function x of t and y of t. All right. We can study, so far my examples have all been kind of just moving from one place to another. We can also do motion where I start here, I drive to there, and then I turn around, I drive back. And then maybe I drive somewhere else, and then I drive back, right? So maybe this place is home, this place is work, maybe this place is the grocery store, right? So I'm starting at home, I drive to work, and then I drive home from work. And then from home, I drive to the grocery store, and then I drive home again. So I can describe that as well. Any sort of motion you can describe in this way. And again, once you have these formulas, you can with using those formulas. All right. So again, the most kind of straightforward parts of the motion is maybe your velocity, your acceleration, and so on. Okay, so hopefully this gives us an idea for why we care about this topic, right? This parametric equation topic. We need both these equations to describe, right, our position in the real world, because our position in the real world consists of, right, east-west, which is we think of as the x, and north-south, which we think of as the y. And of course, if you actually want to describe actual real-life motion where you have a z-axis where you can jump up and down, right, or if you're flying in an airplane, you would actually add a z of t equals whatever, and that would describe your altitude. All right. Okay, but we're restricting ourselves just to two of them, x of t and y of t. All right, so one question we can ask is, let me write down another, or let me use the same example I had up there. So 1 plus 3t, 2 plus 5t. 1 plus 3t, y of t equals 2 plus 5t. All right, so one issue is that when you have a parametric equation like this, right, describing some sort of motion as time passes, just looking at these two equations, it's hard to tell what kind of motion this is, right? Does this describe driving along a straight line? Does this describe driving in a circle? Right? Does this describe driving somewhere and then driving home, like this last example, picture example that we gave? Right? So the question is, what graph does this guy, or yeah, what graph does this guy describe? Right? What kind of motion is this? Right? If I were to draw our motion, what does it look like? Okay. Well, I've told you that it's a line, but how did I figure that out? Right? That's one question. So one brutal way to do it, which is terrible, is to just plot all the points, right? So I do what we did earlier, right? At time t equals 0, I plot the points. I plug in t equals 0 for x, t equals 0 for y. I get 1, 2, so I know I start somewhere there, right? I plot t equals 2. I know I'm there. Plot t equals 3. I plot t equals a half. Right there, I plot t equals 2.7 right there. And then from all these plotting, I can kind of get an idea for how I moved, right? But plotting points in order to kind of understand a function is super, super dangerous because, right, if I plug in t equals 0 and I know I'm right there, I plug in t equals 1, I know I'm right there, right? How do I know what happened between time 0 and 1? Right? How do I know I just moved in a straight line from t equals 0 to t equals 1? I don't, right? So when you plot points, you don't get information about your function between the points that you plotted. And your function could go crazy in between those points, right? That's why, it's always really important to understand the graphing techniques whenever you have one in a math class. So you'll see one in calculus, a very important one. And if you're doing pre-calculus next, you'll see a graphing technique in pre-calculus, which is essentially the same as the one we did in our class when we graphed sine and cosine functions. All right, so this is terrible, right? Just plotting points. So how would I actually figure out that this was for sure a line? So the way we do this is you take a look at these equations. So let me rewrite them again. And oftentimes we express these without writing x of t and y of t. We just write x equals 1 plus 3t, y equals 2 plus 5t. And we just implicitly remember that x depends on t and y depends on t. All right. The book likes to do this, but I always like to write x of t and y of t just to always remind myself that x is a function of t, y is a function of t. Therefore, if I want to study my motion, I study the function x, the function y, and I can apply all the knowledge of functions to studying this. All right. Okay, so in any case, let's write it as without the t's, x of t, y of t. It's just x equals and y equals, right? Now, what we're going to do is we're going to get rid of the t's in this equation. All right. When we get rid of the t's, we're only going to be left with x and y's, a relationship between x and y's. And then we'll often be able to tell exactly what that object is. All right. It sounds kind of weird, but let me actually just do it. So I'm going to take this first equation, x equals 1 plus 3t, and I'm going to solve for t, right? So solve for t. So what I'm going to get is x minus 1 is equal to 3t. Just throwing the x, let me write the original one also. X equals 1 plus 3t, right? That tells me x minus 1 is 3t, which tells me t is equal to x minus 1 over 3. All right. Let me simplify that like this. X 1/3 x minus 1/3. Okay. All right. What am I going to do with that? Well, because I know t is equal to this guy in terms of x, that means I can take the second equation, and every time I see a t, I can replace it with 1/3 x minus 1/3. All right. And what that's going to do is going to give me a relationship between x and y, and that will tell me oftentimes what my drive looked like in a way, right? So let's do this. So using my second equation, which was y equals 2 plus 5t, right? I'm going to get y is equal to 2 plus 5, and then again, every time I see a t, I replace it with 1/3 x minus 1/3. Okay. All right, I'm going to simplify this so that I can recognize what this is. This is 2 plus 5/3 x minus 5/3. And let me simplify that. 5/3 x, and I'm going to combine the 2 minus 5/3. That's going to be 1/3. Okay. So ultimately, what I have here is an equation in terms of just y and x. All right. And that equation is something we hopefully recognize. This is a line. It's a line that has slope 5/3. And it has y-intercept minus 1/3. Okay, so what this tells me is that my drive, in a way, was along a road that had y-intercept here, and it has slope 5/3, so something like this. Okay, so this formula represents, in terms of kind of the intuitive description or our picture description of what's going on in terms of motion, this is the road we're driving on. Okay, so in other words, we're driving on a line. All right. Okay. One thing important to note from this is this final equation here. This actually is not. This only describes. Let me say it like this. This only describes the road that we're on. It doesn't describe how we're driving along the road, right? So once I've gotten rid of the t's in this equation, at this step right there, then I've lost all information about my actual motion, right? In other words, if I just look at this equation, y equals 5/3 x minus 1/3, it's lost information about whether I was driving in this direction, or whether I was driving in that direction, or whether I was driving in this direction, then turned around and started to drive in the opposite direction, or anything like that, right? I'm only describing the road that I'm on. Okay, so maybe one way to think of this is once we've done this procedure, this describes the road, whereas our original set of equations describes our actual motion. All right, so that one encompasses much more information. All right. All right. However, describing the road we're on is useful because I was able to recognize that this was a line. So now I know I'm driving along a road that where the road is going roughly northeast, southwest. All right. Okay. Let me do another example. Oops. So let's say we have a motion and or a parametric equation, and let's say this time it's x plus 1 and t plus 1, function of t, right? And this second one is t squared. Okay. All right, so again, this set of equations describes my exact motion, right? If I wanted to know where I was at time, where I am at time 4, right? I just plug in 4. So at time 4, we're at 5 comma 16, for example. All right, just plugging 4 into the first equation, 4 into the second equation, giving me the xy coordinates. All right. The question is, again, let me phrase it kind of using the same terminology we used just up there. What's, let me write like this. Describe the road we're on. Okay. All right. In other words, what's the graph of our motion? Okay. So again, we do this in the same way. X equals t plus 1, y equals t squared. Let's use the first equation to solve for t. So t equals x minus 1. And then let's plug that into the second equation. Y is equal to x minus 1 squared, whole thing squared. All right. So this guy here, that describes the road we're on. All right. And what is that? Hopefully we recognize that's a parabola that's been shifted to the right by 1 step. So like that. All right, very roughly. Okay, so this is the road, right? Again, this y equals x minus 1 squared only describes the road. It doesn't describe our actual motion along the road, right? Whereas our original equations here describes everything, right? It tells me where I am exactly, precisely at any time. So if I take a look at this and I, just think about x of t versus y of t, this actually, looking at the two equations up there, this actually describes motion along this parabola, driving in that direction. All right. Okay. Let me do one more. So x of t equals t cubed, and y of t is equal to t minus 3. All right, or let me do a different number, t minus 4. All right, so again, we want to get rid of the t's and end up with just an xy equation. And again, that describes the road that we're driving on. And the way we're going to do this one is a little different, because we notice the description of y in terms of t is fairly simple. So it's really easy for me to solve for t using the second equation. So this time I'm going to use the second equation to get my t, to solve for t. All right. So you don't have to always do the x first. This one I'm choosing to work with the y first. So using this equation, the second equation, I end up with t equals y plus 4, right? And then plugging this into the second equation, x equals t cubed, or the first equation, sorry, that tells me x is equal to y plus 4 whole thing cubed. All right. And again, this gives me a relationship between x and y. And if I can graph this relationship, or I know what this relationship describes, then that's exactly a description for the road that I'm driving on. All right. So actually, this one is, let me draw x here, y there. And this one is going to look like, that. All right. So this is the road that I'm driving on, or driving along. All right, but again, this is merely the road, this equation, this x equals y plus 4 cubed. If I want to know which direction I'm driving, how fast I'm driving, whether I'm accelerating, whether I'm turning around, whether I've stopped, I need to analyze it via the original equation. All right, and if I did do this analysis in this particular example, we would see that we're driving in that direction, all right, the whole time. So there's no turning around or anything like that in this example. All right, let me do one more. So what if we had something a little more complicated, x of t equals sine of t, and let's say y of t is equal to sine squared of t. All right. Okay, so of course, when you do have functions, they can be very complicated. The ones we have been looking at, right? Always one of them, either the x equals or the y equals, have been fairly simple. In the previous example, y equals t minus 4, fairly simple. So we easily solve for t, right? But here for both of these, both guys are really complicated, sine t, sine squared t. But what we can do for this example is instead of solving for t, we notice that this first one is sine t, x is sine t, but y is just a square of that, right? So thinking about that, that means that y is, let me write them again, x equals sine t, y is equal to sine squared t, right? Just noticing x is sine t, y is sine squared t, so y is equal to x squared, right? So what this ultimately tells me is that I'm driving along a parabola. Okay, so my road is shaped like this. All right, so while in a way, ideally, you actually solve for t and then you plug that into the other equation like we did in the previous examples, sometimes it's not going to be as easy. And then you have to do kind of other kinds of analysis. And here the analysis was just noticing sine squared of t is just x squared. All right. Okay, so this one, again, we're driving along a parabola. But this motion is actually interesting because if I actually study the motion up here, right, even just in a simple way by plugging in values of t, you'll notice that at t equals 0, we're at 0, 0, right, because sine 0 is 0. And as time passes, what's going to happen is we're going to be moving up to here, maybe to some point right there, right? And then we're actually going to turn around and drive back, right? And the reason behind this is because sine t and sine t is periodic. And so when you follow the graphs here, or you follow the instructions here, sine will oscillate, right? So you're going to be going from sine of t equals 0 to sine of t equals 1. Right? Let me actually draw the picture for sine, right? Sine looks like that. So you're going to be driving your x position, for example, will be getting bigger and bigger and bigger. But once you hit the time pi over 2, your x position will be getting smaller and smaller and smaller. So what's effectively happening is you're driving, t equals 0 is here, t equals pi over 2 is right there. And then you're driving backwards. You're driving back to where you started. And then you're driving forward again, and then back where you started again, forward again, back where you started again. Okay? So while we're driving on this parabolic road, parabolically shaped road, the sine t and sine squared t precisely tells me how I'm driving along it. And the answer is I'm going up there, and then I'm driving back. And I'm going up there, and I'm driving back. All right? And so on. So maybe this describes a few days in my life, right, of starting at home, driving to work, driving back home, and then driving to work the next day, driving home again, and so on. All right. So very complicated types of motion can be described using this this idea here, this parametric equations or parametrizations idea. All right. Okay. This is a trig class. So we had sines in this example, but let's do one that's very related to trig. Let's do a final one, x of t equals cos t, y of t equals sine t. All right, this one is really important because, well, let's take a look at what the road is. So here, again, solving for t is going to be a huge mess because t is equal to what? It's going to be arc cosine, right? If I want to get the t, if I need to solve for t. And an arc cosine is a big mess because we know from studying the inverse trig functions that they're only defined for limited values. So here is like the previous example, we have to kind of be a little clever about this in order to get the relationship between x and y. And here we notice that, well, x is cos t, y is sine t. And so that means x squared plus y squared is equal to cos squared plus sine squared of t, right? But what is that? We know that's always going to be 1. And so I end up getting the relationship between x and y, again, without the t's in it anymore, and it's a circle, right? It's a circle of radius 1 about the origin. All right. So this set of equations here, this parametric equation, describes motion along a circle, right? Along a circular road, let's say it like that, all right? And again, if you analyze this a little closely, for example, when time is 0, we're at the position cosine 0, which is 1, comma sine 0, which is 0. So we're starting out at time 0 here, okay? As time passes, what's happening is if you plot the points, for example, at time t equals pi over 2, cosine pi over 2 is 0, sine pi over 2 is 1. So we've moved to here. This is at t equals 1. And if you do, you think about what's going on in between, this is going to be motion along this circular road like this. All right? So it's counterclockwise motion along a circular road, along a circle. All right? Okay. So this is really powerful because working with circles is generally not so easy, because when you want to describe a circle, right, in terms of even just x and y, and you want to work with functions, then you have to solve for one of them, right? So you might solve y squared equals 1 minus x squared, and so y is equal to plus or minus square root 1 minus x squared, right? But this is not a function because this y has a plus or minus there, so for every x, there's actually 2 possible y's. So it's really hard to work with the circle in this way. But now we know if you want to work with the circle, alternatively, you can study these two equations right here, this set of equation right there. All right. Okay. As a small note, if I have x of t is equal to, let's say, 3 cos t, y of t is equal to 3 sine t, then x squared plus y squared is going to be 9 cos squared plus sine squared. So it's just going to be 9. So this guy, this guy right here would describe motion in a circle also, except the circle has a bigger radius 3. All right, it would still be counterclockwise motion. So this number right there effectively tells me the radius of the circle that I'm moving around. Okay, a good question to maybe pause and think about a little bit is, what if I want to drive along a circle of radius 3, right? But this particular example here, I'm driving around counterclockwise, right? What if I want to drive clockwise? How would I change my equations? How would I change my x of t? How would I change my y of t to make it so that I'm driving clockwise? All right. So that's one thing you can think about for yourself. Another thing you can think about is, what if I want to drive faster, right? So in this example, at time t equals 0, I'm going to be right there. At time t equals pi over 2, I'm right here, right? What if I want to drive twice as fast, right? What if I want to get here at time t equals pi over 4, right? So that would be twice as fast. How would I change these two sets of equations? How would I change x of t and y of t so that I could drive twice, double the speed, right? I want to know these because right, as the equations that I have right here only describe specifically the motion counterclockwise, right, around a circle of radius 3. But maybe I do want to drive clockwise, or maybe I do want to drive faster, or maybe I do want to drive slower, and I want to study that, my motion using math. Then I need equations for describing those. All right, so think about how you would modify these two equations here, to describe whatever motion that you want, right? Clockwise motion, faster motion, slower motion. Maybe a fun one would be, what if I wanted to, instead of starting at 1, 0, right? I wanted to start at, instead of starting at 3, 0, I wanted to start at minus 3, 0, right? I want to start t equals 0 to be right there instead. How would I change this, my sets of equations, right? And an even more interesting one that you can think about is these are circles, the two examples I've given are circles about the origin. What if I want to describe motion, let's say counterclockwise, around a circle that's not about the origin? Let's say I want this circle to be with center 4 and 4 comma 3, and let's say the radius is 2, right? Or let me not use 2. Let me do let me make this a 5 here, and let me make this just so my picture is kind of consistent. So 7 here, 5 here, and radius 2. All right. Otherwise, it would have to cross the what I had originally. It would touch the x-axis, but the picture I drew wasn't. So here's a question, right? How would I describe a motion moving counterclockwise around this circle with center 7 comma 5 with radius 2, right? And again, you want to kind of start with the core idea of cosine t sine t, but you need to modify it because cosine t sine t always describes circle around the origin. All right, so that's a fun set of problems to think about. And if you can figure those out, then probably you understand kind of how this these parametric equations or these parametrizations work. Okay, so these equations, let me say it like this. So the kind of these other problems I've just described are kind of a different direction of looking at, or different point of view for looking at parametric equations, right? So when I say try to find the parametric equation that describes motion counterclockwise about this circle right here, right, about this circle right here, then what I'm actually doing now is starting with, in a way, with the road, and then asking you to give me some motion that describes motion along that road, right? Previously, we've always started with the motion, and then we've tried to figure out the road. So this opposite direction is super, super important because normally when you want to study a graph, right? So normally if I want to study, let's say this guy right there, right? I want to study this mathematical object. Then I can describe it as y equals x squared, right? So here, if I describe it like this, I can think of y as a function. I plug in x and I get the output x squared, right? I often want to do this because there's a lot of techniques for understanding things through functions, for understanding functions. So anytime I can describe something in terms of a function, then I can study it very, very easily, right? Especially using techniques from calculus. All right, because calculus, the idea behind calculus is it allows me to study functions. So once you've learned calculus, everything you want to do, every math problem you want to solve, you want to think about how can I transform this problem into a problem about functions, right? And then you can use the techniques of calculus to study it. So here, if I want to understand the parabola, I want to write it as a function, right? Y of x equals x squared. Okay, so no problem here. This is easy. What happens if I want to describe a line? Or what happens if I want to study a line, right? Well, I describe it as y equals whatever, 3x plus 5, something like that. Okay, so here again, I can think of this as a function. Y of x is 3x plus 5, right? And I study this function right there. Okay, now this is great for these two examples, but what if the thing I wanted to study, the mathematical object I wanted to study, wasn't a parabola like this, or wasn't a line like this, but instead was something like this, right? Maybe it intersects itself, maybe it goes around in circles, something like this, right? This guy here, I can't do the same thing that I've done above and write it as y of x equals something, because this picture here cannot be the graph of anything, right? Because if I write y of x equals something, that's a function. But for a function, right, functions have to satisfy the vertical line test. But this one, of course, it passes through the vertical line many, many times. Okay, so I'm not able to write this mathematical object here, or this curve, I'm not able to describe this curve in terms of a function y of x equals something. So instead, if I want to describe this curve, I think of this curve as a road, right? Just like with parametric equations. And I describe it as x of t equals something and y of t equals something. Okay. Now this makes it easy to work with mathematically because this first guy is a function. The second guy is a function. And you can apply all the techniques of calculus to study this curve via studying the function x of t and y of t. All right. Now, of course, you do pay a price in that you have to study two functions, right? Whereas in the previous examples, you only had to study one function each. But there's nothing you can do about that. This particular curve is so complicated that you're forced to study two functions in order to understand it, in a way. All right. So this idea of kind of starting with a road and then figuring out equations that describe motion along the road, in other words, figuring out the x of t and the y of t, is very, very useful for studying the road, right? So again, this is kind of the inverse problem to what we have been talking about. Okay, so this is exactly the kind of problem I mean when I say find a parametric equation that describes this circle here, that describes motion along this circle here. Okay. All right. So how do we do these kinds of problems? Let's start with kind of the more basic type of problems. So let's try to describe a line first of all. All right. So let me write kind of the official math words here. A parametric equation. Oops. Describing or let me write it like this, where write a parametric equation of a line where t equals 0 corresponds to 2, 1, and t equals 3 corresponds to 3, 4. All right. Okay. So again, this time we're going backwards. We know we want to work with a line already, and we need to describe the x of t, and we need to describe the y of t. All right, so I need equations for this guy and this guy right there. I need formulas for that guy and that guy. Okay, so the way we do this is we think back at our previous examples, and we notice that anytime something looks like this, x of t equals a plus bt, a and b are constants, y equals c plus dt, c and d are constants, that describes a line. All right, if whatever a and b are, c and d are, this describes a line. Okay, so all I have to do, so this is in a way we could say this is the generic equation, parametric equation for lines. All right, so if you need to describe a line, you use this form. All right, so what if we want a specific line, right? The line where t equals 0 corresponds to 2, 1, and t equals 3 corresponds to 3, 4. Well, we solve this these equations for a, b, c, and d. All right. So for example, t equals 0, we know we should be at 2, 1. So that's the same as saying x of 0 should be 2, and y of 0 should be 1, right? 2, 1. But on the right-hand side, we know x is a plus b, x of 0 times 0. And then y of 0 is c plus d times 0. All right. Well, b times 0 is 0, so this is equal to a. This is equal to c. So instantaneously, we know that a should be 2 and c should be 1. All right. And so let's update our information here. X of t is equal to 2 plus bt. And y of t is equal to 1 plus c dt, sorry. Okay. All right, now we need to figure out what D and C and D are, or sorry, B and D are. So we use the second bit of information, the t equals 3, right? X of 3, we're told should be 3. And y of 3, we're told should be 4, right? The formula for x of 3 is a plus b times 3, right? We just figured out a was 2, so 2 plus b times 3. And then the y should be 1 plus d times 3, right? And looking at these individually, the first one tells me 3b is equal to 1, and so b is 1/3. The second one tells me 3d is equal to 3, and so d is equal to 1. All right. Okay, so now putting all our information together, we got x of t is equal to 2 plus 1/3 t, and y of t is equal to 1 plus t. All right, so this is our equation, or our parametric equation describing our line. Okay, so actually you'll notice something very useful here. Remember that normally we think of lines as y equals mx plus b, right, in slope-intercept form. So this describes a line with intercept b and slope m. But this form, remember, it doesn't work at all if you have a line that's vertical, right? Because when you go and try to figure out the slope for this, it's going to be infinite. You're going to be dividing by 0, right? So if you did want to work with a situation where any kind of line could arise, right? Not just necessarily always the good ones, y equals mx plus b, but where vertical lines are also legal, then you can't count on y equals mx plus b to be an equation that describes everything, right? So how would you do it? Well, this parametric equation business can describe any line, right? So if I want this vertical line, for example, then can be described, well, x of t equals something, y of t equals something. Well, if we just want to describe the vertical line, we notice that this vertical line, let's say at position 3 like this, every point here has the same x coordinate, right? So maybe this is 4 comma 3, this one might be 6 comma 3, this one might be minus 3 comma 3, something like that. Every point here, sorry, 3 comma whatever, right? 3 comma 4, 3 comma 6, sorry about that, 3 comma minus 3, right? They all have the x coordinate 3. So in effect, what's happening is your x of t is always 3, right? No matter what. No matter if you think about this as a drive along this road, your x position during this drive is always 3, right? And your y position, you can just use t to describe it. And then this would be a parametric equation for the vertical line that passes through x equals 3, all right? Or that has x equals 3, all right? So even though parametric equations are kind of complicated in that you do have two functions to describe the object, the curve, there's a lot more flexibility, right? I can describe any line as opposed to describing with y equals mx plus b, describing only lines that are not vertical. All right. By the way, I chose y of t is equal to t arbitrarily. If I had chosen y of t equals 10t, that would have worked as well. And in fact, what that describes is motion that's 10 times as fast, all right, along this line, going north. If I want to go south, I could use y of t equals minus t, right? Then I would be driving south. If I want to start at a different position, if I want to start at t equals 0, I want to be at position 1, then I can use t plus 1, right? Then at time 0, I get y equals 1. Okay, so that's how you could kind of modify your motion for this example. Okay, so super powerful, all right? Okay, so let's try to figure out parametric equations for a few other curves. So one big class of curves are ones that are described as y equals something, right? So y equals something in terms of x. So y equals x cubed, all right? So these are fairly simple because they are curves that every x position corresponds to a single y position, right? So what I can do for these is just to use x of t is equal to t, right? And if I have x is equal to t, what should y be? Well, literally that describes what y should be, right? X of t is equal to t, so that means y should be t cubed, right? And so y of t is equal to t cubed. Okay, so when you have a description of a curve where already one of the variables is in terms of the other one, then it's very easy to write down a parametric equation for that curve. All right. Okay. Anything, this works with anything. If I have a curve y equals sine of x, right, this would be a curve that looks like that. Or in other words, a road that looks like this, right? How would I describe motion along this road? X of t is equal to t, y of t is equal to, well, if x is equal to t, then y should be sine of t. All right, and that's it for that one. Okay, so when you have one function in terms of the other, it's super simple. Now this is even the case if I had my equation where y squared is equal to x, right? So what is this? This is actually a parabola that's sideways, like that, right? How would I describe this in terms of a parametric equation? Well, again, this one here, if I read this kind of from right to left, x is equal to y squared. So if I do y of t is equal to t, kind of the opposite way, then x of t has to be y squared, right? And y is t, so y squared should be t squared. And so that would describe motion along this sideways parabola, okay? All right, and again, in this particular, with this particular parametrization, I would be moving, I would be at t equals 0, I would be here, and I would be moving in that direction. So this would describe, again, you always want to keep in mind what's the motion and what's the kind of the road. So here, y squared is equal to x describes the road, and this parametric equation describes the actual drive along the road, all right? Okay, so let's get back to the circle. If I wanted to describe x squared plus y squared equals 16, right, that's a circle of radius 4, we've already kind of seen that something like this is going to work. Right, because if I square x and I square y and I add them together, this will give me 16. Okay, so this guy here is a parametric equation for a circle of radius 4 about the origin. But sometimes we only care about a portion of the curve, right? So here, let's say we have the additional condition that we don't want to describe the entire circle. We only want to describe, let's say, the portion of this circle that lives in the second quadrant. Let's say right there. I only want to describe this guy, this portion, all right? So how do I express that in the parametric equation? The way to do that is to give restrictions on what t I'm allowed to be working with, right? So what happens here is I know that that point right there, this is going to be, my radius is 4, so this is going to be 0, 4, right? When am I at 0, 4? That's going to be at t equals pi over 2, right? So this corresponds to t equals pi over 2. When do I hit this point during my drive? This is going to correspond to t equals pi, right? Because when I plug in pi, I get 4 cosine pi, comma 4 sine pi. Cosine pi is minus 1. So I get minus 4 here. So x coordinates minus 4. And sine of pi is 0. So minus 4 comma 0. All right. So in order to describe just this quarter circle, just the part of the circle in quadrant 2, I would restrict my t to be between pi over 2 and pi over, and pi. All right. Okay, so, if I wanted to describe, for example, this circle, but all the parts from here all the way until there, right? 3/4 of the circle, but not the part in the first quadrant, then I could use the same exact parametric equation, except my t would, in this case, be pi over 2 to 2 pi. All right. So let me write same equations, but this time t has a different restriction. All right. So these kind of restrictions on my t give me restrictions on what portion of the road I'm interested in. All right, so we can do this, not just with these circles. We can do it with any of these. For example, up here with this y squared equals x, this sideways parabola, what if I was only interested in the lower half of this parabola, right? Then the lower half would be, well, right there, at that point right there, that's t equals 0. And then I notice that for negative t, I'm going to get negative y, right? So that means that I'm only interested in minus infinity to t to 0. That would describe just the lower portion of this sideways parabola. Okay, so super useful if you're only interested in some portion of your curve. All right, finally, let's give an example that kind of ties into polar coordinates that we talked about last time. So what if the curve that I'm interested in were y equals cosine of 2 theta, for example? So this guy is going to be the picture of this curve, or this road is going to be like a flower like this, right? We talked about, like that, right? How would we describe this with a parametric equation? So this one is more complicated, but if we think about it in 2 stages, it's actually relatively simple. So the idea here is you have your r and your theta, right? But the r is described in terms of theta. So in a way, this is very similar to the equations, to the problems above, where we had the, for example, the y is described in terms of x, right? One variable is described in terms of the other. Y is equal to sine x, or x is equal to y squared. So here we have r is described by theta, using theta. So in the same pattern as above, we know that if we let theta equals t, right, just like up here with y equals x cubed, we let x equals t, and then that gave us y. Y had to be t squared. Okay, so here, if I say theta is t, then that gives me r. R has to be cosine of 2t. Okay, now generally, at least in our class for this section, we want our parametric equations to all be x equals something, y equals something, right? That's not what we have here. We have theta equals something and r equals something. But what we can do is move to a second stage of the problem and translate the r and the theta into x and y's, right? So from last time, polar coordinates, x equals r cosine theta, y is equal to r sine theta, right? And so we can translate this into t's because we have the formulas for r and theta, right? R is cos 2t, so this is cos 2t. Cosine theta is cosine of, theta is t, so cosine of t. Okay, and then y is equal to r sine t. R is cosine 2t, so this is cos 2t. Oops. And then sine of theta is, well, theta is t, so that's just sine of t. Okay, so if we do this in 2 stages, it's really simple, or at least each stage itself is fairly simple. Okay, so this would be ultimately my parameterization would be x of t is equal to cosine 2t, cosine of t, y of t is equal to cosine of 2t sine of t. Okay, and again, this is super useful because studying this flower right here is not necessarily very easy using polar coordinates, right? Because polar coordinates are not, we're not as intuitive. We don't have as much intuition for polar coordinates. Studying it in terms of x and y is going to be a horrible mess, right? Because we know that this guy here has a very complicated graph. And so x's and y's, the equation relating to x's and y's is going to be really nasty. On the other hand, if we use parametric equations, right, we just have to study these two equations individually. This function here, that function there. Together, analysis of these two functions can help me analyze properties of this flower right there. Okay. All right, so that's all we're going to do in our class with parametrization. But like I said, in real life, each of these parametrizations you can think of as describing motion. And then using calculus, you can pick out from the equations, you can pick out the velocity, the acceleration, the curvature of your motion, all that kind of information. So super practical in practice. And you'll definitely, if you go on maybe say engineering or something like that, or physics for sure, you'll be working with these parametrizations because they allow us to work with very complicated objects via very simple functions. All right.